In this video, I will be presenting the PCB that you can see on the right. So this is a dual switching regulator, which takes as an input a certain voltage and outputs a 3.3 volts and a 5 volts voltage, which are used to power the main board, which we can see on the left. So it is connected on this port of the main board through this connector. And this PCB provides many layers of protection, being an independent power supply. So each of these of the board on the left will have its own power supply, which you can see on the right. So for the overview of the board, you can see how it is on this schematic. So it will take an input voltage between 5.1 and 36 volts. So we can actually have the board on the left working at 4 volts if the input is 4 volts. But the 5 volts channel only works for a voltage of at least 5.1 volts. It then goes through a reverse input and short circuit protection circuit. So this is basically an ideal diode, which I will explain and in more details in this video, and then goes through a dual channel switching regulator, and it also can then go into an overvoltage and overcurrent protection circuit, and then onto the main board. There are also two controlled inputs, which are not shown here because this was for an older version, which you can see here. But as will be explained in the video, these two connectors are not functional in this version, as there was an error during the design phase. But this is something that was not used during the competition, but if did be, should be redesigned for this year. Right, so let's get into the schematic. So the schematic is on a single page. So it's it's a fairly straightforward schematic. So on the top left here, you can see the main connector, which is an XT30 connector. So you can accept both XT30, or you can also put a terminal block if you want. So this will take the input voltage from any source like the battery or a regulated voltage. During the competition, we used a 24 volts regulated voltage. Then we have here the connector for the main board. So this is just the connector that you can see below. So this is a notched connector to be sure that we can only plug it in the correct orientation. Then we have external power control. So the main board can output a digital signal, which are the 3.3 volt control and 5 volt control pins. So if you look at the PCB here for the main board, and you look through the microcontroller, you can see that we have a connection from Meissa, which are these two, and these connections are connected to these pins here. So basically, the pins that are on this connector, the two that are on the top, and these ones are connected to these ones, which are here. So these are basically used to control MOSFETs for output power on the connectors here and here. But during the design phase, I didn't see this when I was designing it, and it really was a very rookie mistake. But here I am doing high side switching, which doesn't work obviously, because you need either a bootstrap capacitor or switch it on the low side. So if you want this circuit to work, you will need to move this MOSFET from this part here to the ground, so more like below here. So if you don't understand why this doesn't work, so we'll do a quick recap of MOSFETs. So let's say that this MOSFET here is non-conducting because the VGH, a VGD, a VGS, this is the source, yes, and this is the gate. So let's say that the VGS is lower than the threshold. Then in this case, this is non-conducting, and we'll have that the 3.3 volts, it will not be connected to this 3.3 volt out. like the drain will not be connected to the source if the threshold is lower than the gate threshold. And now, if this pin goes high, so 3.3 volts, then what happens is that this gate here would be at 3.3 volts. This will be at a certain voltage, and the gate will be greater than the threshold, which means that this will be conducting. But now there is an issue, and the issue is that because this will be conducting, and this is at 3.3 volts, then this output will also be at 3.3 volts, and this input here is also at 3.3 volts. So the difference in voltage is actually now 0, which means that this will not be conducting anymore. So we will have some kind of balance between conducting and non-conducting. So this means that the voltage here will be such that the gate will find the right spot where the gate to source voltage will find the right spot such that this MOSFET will be partially conducting. And this is not what we want for this application. So as I said before, if you want this circuit to work in a future iteration, you will need to move this MOSFET here down on the ground pin so that you can control it with low side switching and not high side switching. So yes, so this is one of the things that must be changed in order for it to work. Right, so now let's go into the reverse input protection. So for this, we use an automotive grade ideal diode. So this ideal diode controller has multiple layers of protection. So it can protect against short circuit, reverse voltage, and other types of protection. So this is very, very useful. It controls an external MOSFET and can also protect against the voltage transients. So this is a very cool chip. And if you want more details about the selection of the passives and such, you should read the datasheet. So you can press D once you are on the component to read the datasheet. So I've basically followed most of the datasheet for this component. So it is very straightforward. We have the same components here, and we have the bulk capacitor and the diode for protecting the gate of the MOSFET. So this is a very classic setup, just following the datasheet. Okay. And now for the most important part of that circuit is the dual channel switching regulator. So for this, we use this MAX 2457 chip. So again, you need to pay very close attention to the type and the model that you are using. So in this case, we are using the ATIF model. And the ATIF model is the model that outputs a 3.3 and 5 volts channels. We had some issues in the past where we ordered the wrong one, which did not have these two types of channels. So here, if you look for the type, which is ATIF, TIF maybe, I don't know why. Oh, this is not a searchable document, but normally there should be a part somewhere where it's written the type of ordering information that you can have and the different types of chips that there are for this particular family, and you should choose the right chip and not have the wrong one. So here you can see that in our case we use the ATIF, which has a 5 and 3.3 volts output at 2.1 megahertz. So this is exactly what we want. There could be other ones that work, like the IE could work. This one could also work, but it has a lower switching frequency, which we don't want. So this really is the best one to use, the ATIF. Okay, so for the routing part, I will explain it later, but we simply followed either the datasheet here or the evaluation board routing. So yeah, the schematic is quite simple. We just follow the datasheet. So we have here for these two pins, both a bypass and a bulk capacitor. We have, of course, our feedback loop from the output here. And then we have the inductance and the capacitor, which comes back to the circuit. Here we have the feedback loop, FP1 and FP2. Um, so this is a very simple switching regulator setup. It's just that we have a very convenient form factor because this is a chip that has like 2 switching regulators inside. And this chip also has 2 pins which we can use for look for status. So these are open drain outputs which which can be used to control MOSFETs. So we just need to pull them up to a certain voltage, like 5 volts in this case, and they will control this IC here, which is a dual channel N MOSFET, and is used to turn on the LEDs. So here I put some calculation for the different selection of passives and the different parts that we need to choose. So if you want to have more detail about the exact component that I've chosen, you can always go like click E, just select the component, type E, and there will be the manufacturer number and other useful information. So now here at the bottom right, you can see also some more information like the absolute maximum ratings of that PCB, the output capabilities from in terms of amperage and in terms of the limits for the fuses and stuff. So yes, so this is it for the schematic. So now let's move on to the PCB design, which is also fairly straightforward. So this is a 4-layer stack up. So why 4 layers? The initial version that I've described in this document that I will also share. So it's this document that I will also share in the description. Used a 2-layer stack up, and we actually observed a very good results. So we have some scope shots. I don't know where they are, but we have some scope shots which show the performance of our PCB design. But because it was not that much expensive, that much more expensive to have a 4-layer PCB, we decided in the last iteration to use a 4-layer PCB to have better return current path and just a better signal integrity, which allows us to have even less noise. So here you can see the different waveforms for the 3.3 volts and 5 volts channels. So let's have a quick look at this. So let's say that I give it a 5.1 volt input voltage. So this is the minimum voltage for the 5 volts channel to work. We see that we have a dropout of around 200 millivolts, which means that this voltage is at around 4.9 volts, which is enough. And now if we have a 24 volts input voltage, which is what we use for the competition, you can start to see the switching regulator, the switching pattern. So we can also have you can also see the standard deviation for the different voltages that we have, and the same can be said for the 5 volts one. And so yes, so this is the waveforms that we have at the output. And I've also tested it with a power resistor to check how much current we have. So with the 2.5 ohm resistor on the 5 volts, on the 3.3 volts, we will have 1.3 amps of current, and we have a fairly good waveform, and the same can be said at 2 amps for the 5 volts channel. And now for the ideal diode that I showed you before, which protects against short circuit, reverse input protections, and over voltages and stuff. I've also done some scope shots so we can look at how it works. So we can see that when we reverse the voltage, the output is completely flat, maybe with some very slight noise, which means that it can correctly protect against reverse voltages. And here also, if we short the output of the chip, we can also see that the output will be shut down so that we have no damage to our chip. So this is for the functionality. So now let's look into the PCB layout. Right, so as I've said before, we have a 4-layer PCB. So 2 inner ground layers for good return path current, and 2 outer layers. So the outer layers are used for the high current traces because they are in external air, which means that they will have a thicker copper and also cool down more efficiently. So this is the chip in the middle. So there are many different guidelines that you have to follow in order to have a good routing of your dual channel switching regulator. So for example, you want to keep all of the loops as short as possible. So this is very important to avoid having noise coupling uh, like inside of the loops, and also want to have the traces as wide as you can. So um, yeah, there are many different guidelines that you should follow. So for example, okay, I will give some guidelines so that it can be shit. Okay, so now let's move on to the PCB design and the layout of that PCB. So this PCB is a 4-layer board. So we have 2 inner ground layers. This is to really have as little noise as possible, so that we can have very short current path and very good return path. And we have 2 outer layers which are used for high power traces and for some signals. So there are multiple guidelines that have to be followed when you design a switching regulator. So in our case, we want to have, if possible, all components on the same side of the board. So it is mostly the case for all components except for 2 bypass capacitors, which you can see on the back. So this was a compromise to have a very short current path and good decoupling on these pins. And another good guideline that you have to follow in most switching regulators is to minimize the high frequency loop areas. So the high frequency loop areas are basically the switching loop areas. So for example, this loop here that goes through the inductor and through the capacitor back to the chip, this is one of the loops, and we really want to have this loop as small as possible while keeping all of the areas here, the traces as wide as we can, and really keep the loops very tightly spaced together. So, for example, we have to minimize the connection from the output capacitor ground terminal to the input capacitor ground terminal for each buck regulator. So if you look at this PCB here, here the output capacitor would be this. So you can look at this. That would be the output capacitor, and we want the ground terminal of this to be as close as possible to this one. So this is the input capacitor ground terminal. So this is also in the guidelines of that specific chip. So we really followed the guidelines and tried to do the routing to be as close as possible to the reference layout. So another good practice is to minimize the output current loop area. So this is, as I've said before, the one that goes through the output inductor and output capacitor. So that would be for the top buck, that would be this one, and then through these output capacitors here. So we really want to minimize this, and this is very crucial. Then, of course, as in any other design, we really want to place the input and bypass capacitors as close as possible to the relevant pins. So the input capacitors in this case are these ones, for example. And if you look at their placement, you can see that we've placed them as close as possible to the pins that they are linked to. So in this case, the VDD pin here, we have a very short path to the short ground loop here. Not a ground loop, but a short current return path here. And the same can be said on this side. And Another thing is to keep high current path wide and short. So you can also see here, for example, again on this capacitor, we have a very short and wide trace for this output, which is actually where the current goes. We also have very short and wide traces to the capacitors. So this is a very a guideline that must be followed. And then for the feedback lines, so for when you are working with switching regulators, you always have some kind of feedback line, and this feedback is used to regulate, to sense the voltage and regulate it. So we want the feedback signal to be as far away from as possible from noisy switching nodes and high current loops. So in this case, if you look at the feedback lines, which are on the pins 5 and 17, so if you look at 5 and 17, which are here and here, you can see that we've switched layers to try and be as far as possible from the high current loops here. You can see that we've, instead of going on the right here, where the current loop is, I went on the left to really stay away from this high, from this noise. So this noisy current loop. So we go here all the way around and really try to avoid the noisy part of the circuit, and then go through this to this chip again. So I change layers again to have more distance, and the same can be seen here. So for this one, I just go out and then stay away from the noisy loop here of current. I switch layers to be as far as possible, go through this part, and yes, so this is a good routing practice. Then another good layout practice is to keep traces away from the inductor on both layers. So you can see here that I've even set a keep out zone for the inductor. So we want to keep the traces away from the inductor if possible, to avoid having noise coupling into the trace. This is mostly true for analog or very like traces that carry a voltage that must not change. But for digital signals like the control pins here, it's not very crucial, which is why we don't really care here if it's going underneath. It won't really affect much the functionality of the PCB. But we still try to keep it away from the inductor if possible. Okay. And another final thing that must be kept in mind is to choose wisely the width of the traces. So you want them to be wide, but not too wide either, but wide enough so that it can carry the expected current that you want it to carry. So you can calculate or compute the different width for the current using an external calculator. So one that I really use often is the trace width calculator. So just type trace width calculator on Google, and you will find this PCB trace width calculator. And you just need to input your current expectation, the thickness of your PCB. So in my case, it's 35 micrometers. The number of degrees that you want it to have, and then you have the trace length and stuff. So then according to this, it will compute the required trace width. So for example, in my case, it is in external air. Let's say that I want to have 2.5 amps. So we said that in this PCB that we were working at 2.5 amps for the 5 volts channel. So let's put 2.5 amps. And then we see that, oh, I didn't put it, no. So this is 10 degrees, it was, and here 2.5 amps. And here we see that we need at least 1 millimeter in external air of trace width. So if you look at my my trace width for the 5 volts, you can see that the width is around 2 millimeters. So it is more than enough. to carry the necessary current that we want. And the same can be said for the 3.3 volts. So yes. So you can also see that most of the traces for this board were done using polygon pores. So this is a very good way to have large traces with a very controlled shape, so that we can really have very large traces, as large as you can sometimes, and really have a good control over the shape of each of your trays. Okay. So yeah, that's mostly it for this PCB. You just need again to look at um, the different evaluation boards. So I will show you. I will still show you a few ones. So, for example, let's look at the evaluation board for the Max 2457. So I just type this on the internet. So let's type for 2457 evaluation board, and this will give me this board here. So I can then just look through the documents. So data sheets, evaluation kit, and now you can have some examples of how to route this chip. So if you follow this example, and you should have a fairly a board that should be working with no issue. So if you compare the two here, you can see that I've matched quite closely the layout. So you see that we have something coming out onto the inductor, then coming back onto two capacitors, which are here, and the same thing on the other side. So it matches quite closely the system, and this is a very useful tip to have. So to look for the evaluation board, which was actually designed by professional engineers and tested extensively before being sold for us to buy. So the same can be said for this reverse diode protection chip, and not reverse diode, for this ideal diode protection chip. And so yeah, so once you have looked through these data sheets, it should be working fine. Now let's just have a look at the 3D viewer so that you can just have a better look. So this this is the input connector, which is an XT30 connector, and it will output on this connector, and yeah, so we also have here a mounting hole, which coincides, of course, with the mounting hole on this side here, so that we can screw it in place, and it will not move anymore. So it's a very solid way to fix the two boards together. And we also have these two status LEDs, which should be green, or should be lit up if the channel is working correctly. So that's it for this PCB, and normally you should have already watched the main board explanation and the guide through the main board design and PCB layout. So in the next videos, I will be explaining the different other PCBs that we've designed. So for example, the hats, which are plugged on the main board, as well as the motor controllers, the motherboards for the Maxon controllers and stuff like this. So stay tuned and see you in the next video.